Okay, the direction of the acceleration of circular motion. So the direction of acceleration is determined by the change in velocity vector. When we have circular motion, it's kind of like going around in a circle. At a constant velocity, at a constant distance, no, constant speed, at a constant distance from the center of the circle. Okay, so at two different points in time, the velocities would look like that. Let's go back to the notepad here. So acceleration is defined as the rate of change of the velocity over the time. And the rate of change, the change in velocity, is final minus initial, or final is equal to initial plus the change in velocity. So let's just highlight some of the things that I'm talking about here. Once we have the initial speed, that's our initial speed, and our final speed, that's our final. So the initial plus the change is equal to the final. Okay, so our initial and the change is equal to the final. We're given these two. We determine that the change in velocity is occurring right here, and it points towards the center. Okay, so the direction of the change in velocity vector points towards the center. That's why we call it centripetal acceleration. That is center-seeking acceleration. So it's kind of clear here that the change in velocity points towards the center of the circle. But more so, what is that magnitude of that acceleration? Okay, now that we have the direction of the acceleration, which is the same as the change in velocity, what will be the magnitude of this acceleration? In other words, give me the formula. So we have our 2 points here, and it's clear to note that the speed is perpendicular to the radius. It's tangential speed to make it going around in a circle. We saw that little animation here of it going around, and it is perpendicular to the radius. So at both points it's perpendicular. And at two different times we sweep through this angle here, theta. So when I draw the two different velocities and do that subtraction like I did before, this will be the change in velocity. And more so, we need to also take a look at the change in distance. As we take a look at it, this is our displacement. So we got our displacement vector here, or change of r. Okay. Now, these are going to be similar triangles because these have to be at right angles. So if r changes by theta, then v also has to change by theta because they're both at right angles to each other. And the vi and vf are the same magnitude. So these are both isosceles triangles with the same angle between the similar legs. So the geometry is called similar triangles. Okay, so what are similar triangles? Well, if they're the same triangle, different lengths, but same triangles, the ratios would be the same. So what we do, because we want to try to find the change in velocity, so the change in velocity over the velocity is equal to the change in the distance over the distance. The ratios of these will be the same. Okay, so let's isolate delta V because that's what we want. Delta V is equal to V, and then we have delta R. I guess I wrote down delta D here, displacement R, radial all over R. So that's our change in velocity. We'll put this into our change in velocity formula, and we get V over R, and then we have delta R over delta T. Okay, I just did a little bit of shuffling here, keeping the R over the V and getting that, bringing our delta T over here. So V over R, and what's in brackets here is the displacement over the time, because it is a constant motion. this is just v as well, distance over time. So we end up with v squared over r. So the acceleration, the centripetal acceleration, is v squared over r. And we know the direction of these. They're going to be perpendicular. R is there and v is there. They're going to be perpendicular. So it's a scalar equation. It doesn't have vectors over top of it. Doesn't have that because it's a scalar equation, but we do know the direction of both of them. Ta-da!